Hey there guys, and we are back with part 2 of this turntable build, multiplex turntable build. And as promised, here are some 3D printed parts for more of a visual representation, visual representation of what's going on. So down here, I don't recall if in the last stream I actually extended this bottom part here, but this is how originally, and I say originally and I'll get to why, this was originally set up. So this orange gear here meshes with the motor, and that can slide up and down for the multiplexing, and this is full length because it needs to engage this gear at all points. Now there's a couple reasons why I chose to do that, but let's just really quick run through here. I'm not going to hook this up and run this right now just because my spacing here is a bit off, and I think yesterday I said don't really need to worry about spacing, but the more I play with this, I probably should space it out a little bit more rather than just having it on the pitch diameter. So as you can see, imagine the green gear turning here. That turns there. It's going to continue to turn, which is why we need a space in between here so that it disengages the first gear before it starts engaging the second gear. And then when it meshes with the second gear, it starts turning again. Now, a couple things that I should note. These gears are round. I went back and rewatched James Bruton's video, and he did round off his gears. It's one of those things I was thinking, it's 3D printed gears. It really probably doesn't matter, If it clashes a little bit, if it binds up a little bit as it's going, it's just going to move out of the way and then whatever. But it's not difficult to do, and I'm going to one of those things. I did all these modifications, obviously on my own, not on video, which kind of defeats the purpose a little bit of doing these workflow streams. But I'll run back through how that's done once we get back into Fusion. Point being, just I added these features because it really does make a difference to have it be able to slide off into the next gear. So that's one thing I did. The other thing is, as you can see here, depending if it actually fits into frame, we'll see. Let me pull up Stream really quick to see if you're in frame here. Alright, let's slide it back then. Or forwards. Slide that up. Nah, alright. Anyway, point being, I'm not going to mess with the camera too much. Point being that this is very tall. I cut this at 8 inches because this is about 4 inches. These, by the way, are the 5/16 rods. I was calling quarter rods, and I've done that many times before. They're not actually quarter rods, they're 5/16 that I got from work. So this gear, in order to engage at all points during the movement, has to be this long, right? And it has to start out this high, so that by the time we get to the top gear, again, we're going to have 4 different points, so assume that I've got 2 more rods here, and the last one is about yay high. This bottom is still engaging the green gear over here, green gear over there, at this height. So that's why it needs to be about this high. And I said yesterday, well, it doesn't really matter, right? I can make it however big it is. I'm just getting footage for videos. That's all the turntable's going to do. It doesn't matter if it's huge. It matters a little bit, and the reason it would matter a little bit, so this is the plate that I was thinking of yesterday when I was talking about this, and you can see how much larger it is. Again, it is, the better part of 10 inches diameter, something like that. If this plate sits on top of this assembly, it is going to look just fine. It's going to look like a pretty square assembly, and there's nothing going to be odd about it. Now, fact of the matter is that most of the things that I 3D print tend to be a bit smaller, and the plate is kind of overkill. It's a bit overkill. That being said, whether or not anybody really complains about that is another issue. I mean, it's one of those things, unless somebody brings it up, probably most people wouldn't notice. that it's that big. However, while I was getting this plate, I found that plate. And that plate is A, a lot easier to transport and move around. B, a lot closer in size to stuff that I'll be 3D printing. And C, introduces a problem because now all of a sudden we compare that assembly to the plate, and now it's going to look real silly. It's going to look like this plate sitting up on top of a pedestal instead of a platform. So for that reason, it is a lot better to not go this route. And the only reason I went this route is because, as you can see, this is a very simple setup where I am able to just have this one gear like this and go up and down. If I split these two gears apart, they have to mesh somehow. There's a couple different ways I could do that. The quote-unquote simplest is to have some geometry to this shaft that ties the two together. So instead of this free spinning on the shaft, this shaft will now be spinning. And therefore, we're going to be switching over the design to this. This, as you can see, is a D shaft. Well, maybe you can see it. I hope you can see it. It's a D shaft. Obviously, again, this is the same exact rod as this. The reason I was hesitant to do this is because machining a D shaft is not really something I'm set up for, at least on something that would be small enough. This particular, so again, this is going to be 8 inches. This shaft is 8 inches, but the second I switch over to this, we cut off a good 3 to 4 inches, and it will only be 4 or 5 inches tall. That's how it's going to end up. So even though I'm still using the 8-inch shaft, I'm just doing that for demonstration purposes. This shaft, in reality, when we're done with the mechanism, will be shorter. But as I was saying, machining this out of the 5mm rods that I have over here out of scene, I'm not particularly set up for. These aluminum 5/16 rods that I have access to, I feel comfortable enough just running these against the side of an abrasive wheel, which is what I did. They're not perfect, so you'll see here it gets tight at the end here because all I did was take it with a pair of vice grips. I vice gripped one end and then used a pair of pliers to push it up against the abrasive disc, and then flipped it around to the other side and eyeballed it up. Now, for eyeballing it up, the heaviest spot up here is 7.2 millimeters, and the lowest spot, which is down here, is 7 millimeters. So 0.2 millimeters is pretty good to do by hand and eye, frankly, in my opinion. I mean, maybe your opinion differs, but just doing it by hand, I was able to get a decent enough that this will be the path I'm going with. And this, just to demonstrate, one of these things, you're gonna have to imagine here because this is not set out in the correct distance, but yeah, that I was just double checking that I didn't put this gear on the wrong side. This now, instead of having to be long in order to engage at all points, will always be at the same height as this green gear, so it will always be spinning. And then this gear, because it's keyed quote-unquote to the shaft because of the D shaft shape, can slide up and down and still be driven by this gear. So a few things there. One, it only needs one specific gear. Like when I do STLs, you'll only need one gear, one D shaft gear, and that can be both of these, and so that's useful. And two, obviously it's a lot less plastic for a little bit more work to get this D shaft. So those are the advantages and why I'm going to go with it. If I couldn't do this, if I couldn't make a shaped shaft that would transmit power from here to here and therefore utilize this, then that is definitely a way to go. It's reasonable. It just takes up more space. I'm trying to save space at this point because, again, that other plate that I have is a lot smaller, and therefore this size, this 8 inches, stands out like a sore thumb when I put the small plate on top of it. So that catches you up with the things that I've been working on in my spare time, in half an hour last night, and then half an hour this morning before I went to work, and a couple hours after I got back from work, threw all this together. Fortunately, it's one of those things. Printed this guy overnight last night. I designed them up and had the idea. And then these guys, these little gears, these 8-tooth gears, are only 15 minutes-ish a piece at the 3mm, or 0.3 rather. No, wait, 3? It's rough. At rough print speed, it's only 15 minutes to get these, and that's what I did everything here in. One of those things, the details are not terribly important. I may find later on that, it works a little bit better if I print at 2 or 1.5 or whatever. And in the future, I can spend the time printing it. I did not have the time to print it. Like I said, I only had a total of like maybe 3 hours to get everything printed in between last night. Well, again, this was able to print overnight, which was the longest print. But in my free time, I only had about 3 hours to get the rest of the stuff in and off the printer. So I needed to save as much time as possible. But for the finished product, I would go ahead and print these at a lower, at a greater resolution, just so that these curves are a bit more smooth. So yeah, that is all the... Oh, actually, I have one more thing to say before we get back in Fusion. And that is gear ratios. So last night I was being absolutely stupid, and I got the gear ratios wrong because I was being stupid. And I kept on saying 16, 8, 16, 8, and then I said, and then there will be like a 16. We can do a 16 or something like that off the end. It looks like that's showing up alright on stream. Cool. So, sorry, just want to rearrange this really quick. Okie dokies. This is what I was saying, and this is actually correct. What I was saying is correct, however, my brain was being stupid. So, 16/8 is this 16 here to this 8-tooth here. This 16/8 is this 16-tooth here to either of any of these intermediary gears, as we're calling them. And then this last 16 was, whatever output gear I wanted. Again, it could be 16, it could be something else. It doesn't necessarily matter. Now, where I was going wrong and what my brain was actually thinking. If we're doing gear ratios, then we take each of these. This is 16/8. 16/8, and then this 16, depending on how I hooked it up, could be any number of things, whether that 16 is tied to this one, like this gear. So if, for example, I had this multiplex here, and then somewhere way up top I had the 16 outputting, and this was tied to this shaft, that would be one possibility. Oh, actually, one thing I should say. I said D shaft. Let me grab this guy, the red guy. I said you need some shape. That's not technically true. Technically speaking, you could try to put a set screw in here and you just tighten the set screw way down and hope that the set screw holds the gear on a round shaft. Technically could do that. It's one of those things. Plastic with a set screw is not going to hold terribly well if you're just forcing the set screw down. Technically possible, you put a hub on here, maybe you put a threaded insert in, and then you screw, and then you prage. But I don't particularly trust it. That's the only reason why I was insisting that this has to have a shape on it, because this I trust. This is not going to strip out. So anyway, back to the conversation at hand. So if we look at this, 16/8 is obviously 2-to-1. This is 2-to-1. So what I'm actually getting here is a 4-to-1 on the output. So for every one rotation on the input, I'm getting 4 rotations on the output. 4-to-1. That's what that means. That is obviously wrong. I was trying to get a 1-to-1. What was my brain thinking? Well, my brain was being an idiot, and even though I was saying 16-8, 16-8, and then 16 on the end if I want it, my brain was thinking 16-8, 16-8, and it was doing this. 16-8, 16-8. That's an 18. Ignore that one. So I was doing 16 over 8, 8 over 16, 16 over 8. That's what my brain was doing. It was being stupid. If we take this, and then back to that miscellaneous 16 on the outside, if I want the, So this last 16 here, then like that. Again, it was a stupid mistake. I don't know what to tell you. You do this math. This is, let me do that down here. 2-1, 1-2, 2-1, 1-2, if we want it. Obviously, that all cancels out, and we're back to 1-to-1. Again, a stupid mistake, because this guy here is not this. This combination here of the 18th to 16 is not an 8 to 16. It's a 1-to-1, because every one rotation of this is one rotation there. Again, being stupid. And same thing on the back end. When I was saying, if this is tied, you'll recall we were talking, maybe this shaft is tied to an output all the way up top and these are spinning at the same time. That would also be 1-to-1, even though these are not physically combined like this. If they're both running on the shaft and the shaft is spinning both of them, they are still 1-to-1. Again, a stupid mistake, but I figured it out before the end of the stream yesterday, and now we're not going to make that mistake again. So, actually, I don't really need to clean off my desktop, do I, to switch over to Fusion. Don't know why I spent time doing that. So anyway, here we are back in Fusion. You'll see a bunch of extra crap here. That's just me getting models for that 3D model that I printed out. So, first thing I'm going to do really quick is just hide the stuff that is irrelevant, and that includes this big gear. This was the orange gear in our example. I'm going to go ahead and hide that. I'll delete it later, but we are now going with these small gears here. The other advantage here is that I've got 16 to 8, and then in this setup we have 8 to 8 going to each of these gears, which means that as you can, which means that, which means that that's a 1-to-1, so that does not increase the ratio at all, the gear ratio at all. So this has no impact on how quickly or how slowly the gearing is running, and therefore we don't have to worry about it. Now, on to the next important thing. Again, I added these curves to the gear. I want to show you how I'm doing that, because, again, I did that off stream, and that's kind of against the point of the stream. So, I came in here, said, okay, this is just going to be a chamfer. I'm just going to chamfer it. Did this. Went, okay, that's not working. Play with the numbers a little bit. It looks ugly, so came back, added in and all that, and I was happy. That gave me more or less what I was looking for. And once I figured out the number, again, played with the numbers, see what they looked like. I wanted to have some meat here between this little part here, between the tooth and the and the body for 3D printing purposes, because obviously when we print this, the first layer is better to be connected. It's better for the first layer for this to be connected, rather than what the printer would do, which is draw a line here, a little tiny break, another line here, and that little tiny break might have some oozing in it, and then it would draw a circle basically right here, a circular type shape right here, disconnected, and then it's going to try to build on all that. And a lot of times my experience is when that happens, it ends up picking up the first layer. It ends up coming apart because it doesn't have enough surface area to stick to the bed, and then that makes a mess. Excuse me a second while I adjust my microphone up a little bit. A little bit more. Alright, microphone is not cooperating. There we go. It's better at any rate. I'm a little bit hunched over, not that you can see, but we will survive. Anyway. And I hit escape again. I talked about this in the last stream, how I have a bad habit of just jamming escape whenever I encounter anything. 1.5. Again, that's acceptable to me. So I hit OK. Now, obviously we have a circular shape. So very intuitive. Pattern, circle, feature. And then just click that chamfer. I'm going to go ahead and use the pitch diameter because it's a circle centered on our body, so that's fine. And then we have 8 teeth, so if we put 8 in here, 8 copies, that should line up exactly on our teeth because our teeth are equally spaced. If our teeth, for whatever reason, were not equally spaced, we'd be in trouble. But in this situation, we are perfectly A-OK. Now, the important thing here is that sometimes the compute option does not always work on whatever you select. So right now for me, in Fusion, it's defaulting to adjust. It used to default, I'd swear, to optimize. I don't know why it's defaulting to adjust at this point. I just noticed over the past couple weeks that it has been doing that. Again, used to default to optimized. I don't particularly care. In most cases, it's whatever works, and these don't always work identically the same, so I always run through all the options just to see what changes when I do them. As it turns out, the adjust does not work. If I try to hit OK right now with adjust, it's going to give me an error. Identical is not going to work. It's going to give me an error. So our only option to actually make this work, and again, this is something that I figured out last night, is optimized. So I'm going to go ahead and click that, and that gives us all these faces. Now I'm going to back us up a step because what I did last night was I did mirror, features, click these two, and mirrored it across the center line, which I have not drawn yet, but I will in just a second. I made a center plane, a mid plane, and then mirrored it across the mid plane. The reason I am not doing that at this point is because that literally took, so I did it on the 16-tooth one first. The 16-tooth one took 5 minutes for my computer to render, which was a bit surprising. More surprising, the 8-tooth one took 15 minutes to render. So we will not be doing that on stream because I don't want to sit here and fill 15 minutes with talking while it renders. And also, every single time you navigate the timeline back further beyond that point, it has to re-render, which is another 15 minutes lost. So let's get this mid-plane in here that I was talking about. And I'm just doing it before we add the curves, the chamfers, so that I'm 100% sure that it's exactly middle. And I don't accidentally click, for example, this face and go mid-plane some wonky thing. And what I'm going to do now is I'm going to split this. I have the split tool up here there too. I'm going to split the body, get rid of the body, figure out which one it is, remove, and then I'm going to mirror the body instead. Most of the time, I mirror features because that seems more reasonable to me. But in this instance, this will get done immediately. It will render this immediately, as opposed to, again, if I tried to mirror the features for these chamfers, that you and I would be sitting here for 15 minutes. Well, I would be sitting here for 15 minutes. You would click off the video and leave a dislike. So that is how I'm doing the chamfers on the gears. And that catches us up, basically, because everything else is pretty obvious again. I changed this over to this gear. This gear is identical to the one that would be multiplexing these guys, so I'm not going to bother adding another one on here. Because I don't need a full 3D display necessarily. I mean, I might later on, but I want to get through this video since last episode we didn't get through everything I wanted to do, in part because I had a breakdown and couldn't believe how stupid I was, but I want to actually get it through this video, so I'm not going to do any extra steps at this point. So at this point we have a 16 to 8, right? And that's our only ratio. For the outputs, again, as I mentioned last time, we can have a array of outputs on the outside here, or back to now that I'm doing these shafts, each of these then can be tied into their output. It's just the outputs are going to have to be the outputs would have to be above our last input, multiplexed input, because the outputs otherwise would clash with, potentially, depending on their size. Again, it depends what ratio we're looking for the output. But if I got a 16 tooth, let's say on this guy, if this guy is tied to a 16 tooth right here, then as this 8 tooth is coming up, the multiplexed 8 tooth is coming up this shaft, it's going to run into that 16 tooth because it will be overlapping. So we can't really have that. So the easiest thing, again, is to put that on the outside over here. So I'm just thinking where I want to start with here. Again, I'm trying not to, because I want to finish this, make sure this stream gets done, and I've already done a bit of talking. We're already half an hour in. I don't want to do too much extra. So here's what we're going to do. I'm going to rough this out because, again, this is mostly just a design workflow stream. It's not necessarily the tutorial. I'm going to rough out the rest of what I'm doing here, and I'm going to use, pardon me, I'm going to use just 1 or 2 outputs as the example. So at this point, again, as mentioned, we're going to have to output this without interfering with that one back there. So we can go ahead and put another shaft over here, and I will go ahead and do that. Let's create a new component. And output 1 shaft is what I'm going to go ahead and call it. If I recall correctly, last episode we were using not that one. We're using a plane, that one. Maybe not that one. No, it's all set. Alright, we were using plane 3. I'm pretty sure it was plane 3 just to do all our shafts with. So gonna go ahead and do those guys. For this first output, I want this output to be a 1-to-1. Our first output, it was going to be normal speed. That was the plan, right? So in order to get 1-to-1, let's switch back to my desk really quick. All right. In order to get 1-to-1, we already have a 16 to 8, and then an 8 to 8, right? We have fusion. 16 to 8, that's the multiplex gear, and then the 8 to 8 going to each of our intermediary gears off here and here so far. So this is going to be the same for everybody. So all output gears are going to have 2-to-1 and 1-to-1, which obviously multiplies across 2 to 1. So that's the there you go. So you can see that 2-to-1, 1-to-1 multiplies across to 2-to-1. So that's our starting gear ratio. That is obviously twice as quick as the input from the motor. So everything's going twice as quick. So for output 1, our goal is to have a 1 gear ratio. So if we're going to have a 1 gear ratio, we need to get this 2 to 1 times, rather, x over x, or x over y, whatever you want to call that, equals to 1. So this, obviously, this is simple math here. Hopefully you get that. We want a 2 to 1, or 1 to 2 rather, on the output. And one of those things, if you're paying attention, in theory that's an 8 to 16. This 8 is what we're working with right now. That's the last gear that we have right here. So this last gear is going to come up here and be an 8. And in order to get this 2, it has to be 2 times 8, which is 16. So this gear that we're going to work off of is going to be a 16. Now, there is something else that I'm looking at and is probably going to end up happening. And I'm going to draw it to make things, because it's going to take longer to model up in Fusion. Sorry about that. I was just looking at my camera and realized that I had a bit of a dirt on my hands. So anyway, the plan I'm looking at, and back to, I said any intermediary gears are going to need additional shafts. This may or may not be true, depending on what we're doing, because what I'm looking at is finishing off this design. This is our intermediary gear. Okay, instead of going from this intermediary gear to the output shaft with another gear and meshing these two, it would be better. It has a number of advantages. Sorry, got to try to make sure to stay in focus here. It would have a number of advantages instead of going gear to gear to use pulleys. And the advantages there are, 1, the distance is easier to manage, so gears obviously have to mesh. They have to be right there, and therefore the sizes and the placement have to be specific. With a pulley, I can run that pulley a bit farther or shorter depending on my need. Technically speaking, every pulley system has a ratio based on the size difference for the distance between them that is optimal, but you can fudge it a little bit, especially since in this situation, rather than using actual pulleys, I'm just going to use rubber bands. So that makes things, a bit easier. I can just pull them apart, and because they're stretchy, they're extra stretchy as opposed to pulleys, which have a more limited amount of stretch. I don't need to be as precise with the spacing. And basically, the reason the spacing is important on pulleys, to some degree, is that the more extreme this angle is, so let's do this, the less surface contact you have on the pulleys on one side and the more on the other. You want to try to have an appropriate amount of surface contact. So, I'm not going to be able to draw it well, but there's an ideal amount of surface contact and angle that the pulley should be leaving in theory, but again, for this DIY project, it's not going to be that important. So using pulleys gives me that flexibility with how exactly I'm hooking this all up. I don't have to be terribly precise with anything. The other advantage I have, and the reason why a lot of systems use pulleys, a lot of motor-driven systems use pulleys instead of gears, is that if/when something goes wrong, the pulley will just slip. The pulley can slip all day long, and if it breaks, it breaks. It's a rubber band. If there's some binding that happens with the gears are going to shatter. So that's why it's going to be easier for me and better. It has advantages to go with a pulley system attached to the output. And that's everything I wanted to say about that one. So back to Fusion. So right here we have our 8. We need to go to a 16. And I say output shaft 1. I'm going to rename this just to output shaft. We're going to just do the primary output shaft because obviously we're only going to have one shaft to the turntable, to the plate itself, and the mechanism that drives the plate, whether that's wheels or... Here, let me demonstrate really quick. I'll hop back to the camera. That is for the small plate. And that is for the large plate. With that. So the two plates have two different kinds. It still plugs into the D shaft one way or another, and again we'll use a D shaft on the output. And that for that D shaft, I will go ahead and 3D print an appropriately sized D shaft rather than try to get this rod down to the correct size. Although it looks pretty close, it actually may not be that difficult to get this to the correct size. So maybe I take that back. Maybe I do just grind this down to fit inside the inside these pockets. But point being, we can only have one shaft going through these. We're not going to pick this up and slide it over each time we multiplex because that would defeat the purpose. So since it all has to go to one output shaft, that's why I'm going to name this one in Fusion just output shaft. And if I need another shaft to do additional gear ratios on, I will just do that. And then all pulleys will run back to this one shaft on the output. And so I'm going to just keep this. So here's an interesting question, right? These are all going to be meshing like this. Any extra gears are going to be meshing in a flower shape, I'm pretty sure is how I'm going to do it. In which case, and another thing to note, I did 45 degrees here, right? Because these gears are on different levels, they don't need to be separated. I actually could have these closer together if I wanted to. I didn't see the need last night, which is why we were at 45 degrees. I just randomly put in 45 degrees and started flowering them. But as we build out this design, I may need to squish these back together, and they can overlap to some degree. Basically, this shaft size, whatever our shaft size is the limiting factor, because the shaft cannot interfere with the gear teeth. So whatever this point is right here on the very edge, that is the furthest point from the center of the shaft, and that cannot overlap another shaft, and that's our only limiting factor. Otherwise, all gears obviously have to interface with this gear here, and that's the only other thing we got to be concerned about. So anyway, back to what we're doing. I'm going to go ahead and pick the center of this gear back up. Actually, instead of the gear itself, I'll do the shaft, the output shaft on the motor. And I'm just going to go straight across from all that. Just turning off the visibility here to go to the output shaft. I don't know what that's parallel to. Actually, that's probably parallel to that, isn't it? Yep. So let's get this housing rather back in. And again, I'm going to use this edge as a reference for everything. We can turn it off now, and that will be perpendicular to that edge. And then where exactly this shaft ends up is a little bit arbitrary. Since this is the closest one, and this is the one I'm going to call 2 to 1, I'm going to go ahead and throw a 2 to 1 in here. Now this shaft has the gear on it. Again, if I turn this into a D shaft, then that can drive an X-sized pulley. The X size pulley does not have to be 24 millimeters just like this one. It can be any size. It can be 10 millimeters. It can be whatever, right? In which case, whatever size this ends up being just has to be twice what this is. Now, for simplicity's sake and to keep things aesthetically similar, I very well may go ahead and just keep this as 24, in which case this pulley right here, 24 times 2, twice the size, would be 48. And again, I'm just going to keep that. And again, there is a specific spacing, as I was trying to illustrate here, where this is correctly tangent. This is my imaginary pulley, right? This imaginary pulley is correctly tangent to this output, this smaller pulley. What that spacing is, I'd have to do math, and who likes math? Last time I did math on stream, I screwed everything up. So at this point, I'm just going to go 2 inches, 50 millimeters ish, and call it a day. It gives me a little bit of spacing. Let me undelete that. That is not a terrible angle for a pulley right there. So seems reasonable to me. And that's where we're at. This obviously is rod size. And that is good. So let's go ahead and get that output shaft in here. And I will go ahead and make it the same size as the multiplexer shaft, which the size of that, sorry, two-sided, there we go. The size of that is subject to change. We'll figure that out when we get there, when we're done later on. Basically, all right, so again, I can do the math, right, and figure out what that is. So we're going to have 4 gears, right? And they need 1 gear spacing in between each. You know what? I like having this paper because this paper is easy to illustrate what I say. That was that was one thing I was a little concerned with the last stream, was that I kept on trying to explain things, and because I didn't want to draw everything up in Fusion because that would take a while or take more time, I was trying to explain it verbally. But this output shaft, it's quicker to write, is what I'm saying. We're going to have 4 gears. Each of those is 10 millimeters. We know that. So we're starting at 40. And then in between each of those gears, we need at least a 10 millimeter gap, right? There are 3 gaps between 4. 1, 2, 3, 4. So 1, 2, 3 gaps. So 3 gaps times at least 10 is 30. So we know that output shaft is 70 millimeters from the bottom of the first gear. So that's the way we can figure it out. That's the way I'll figure it out later. Again, not necessary to show that in this stream, and therefore I'm not going to resize it. I'm just going to get these sizes set up in Fusion, and then everything else will flow from there. And I am a little bit lost in space. There we go. So there's that. And that looks like a positive number, so I did the correct direction there. And there's that. And there's our new body. So let us go ahead and hop back out here. And here's an interesting discussion. With the pulleys, it would be more ideal to have bearings on the pulleys. Now, I have skate bearings and I have 628s, I believe these are, 623s. I have skate bearings and I have 623s. The skate bearings have an 8 OD ID, if I recall correctly. Yeah. So the skate bearings will actually fit on the shaft, as you can see. So I can actually use these for the pulleys. So if I start with this is 22 on the outside, if I recall correctly. If I recall my numbers correctly, this is 22 on the OD. If I just take that 22 and use that instead of the 24, then that would in theory be fine, but potentially the rubber band has a chance of falling off, unfortunately. There's a couple things I can do there. I can print little discs that I just attach, in some manner to be on either side of this. Obviously, I don't want to glue them like straight down to the bearing because that would stop it from rolling. But I could, glue them to the shaft or do something like that and snug them up, and then we're good, because this will spin and then this will stop the rubber band from falling off. The other thing is to actually make a pulley, and when you're working with flexibles, things that are flexible on a pulley type system, the way you actually want to do that, in theory, is you want the body to be a little bit round, like this. I don't know how well you're going to see that in the picture, but this has a curve to it that bulges out like this. Now, you might think intuitively that you want the curve going the other way, that way it crawls towards the center. That's not actually the way you want it. I've seen this recommended in a couple different resources. One of my bucket list things is to do a DIY, what do you call it? Belt grinder, DIY belt grinder. I heard it recommended when I was looking at that. What's his name? Steve Mold, I think his name is, on YouTube. I saw a video from him. I don't watch much of him, so if I got that name wrong, I apologize. I'm pretty sure the last name is Mold, but I'm not sure about the first name. But I believe I also saw a video from him on that, and I think I saw one other video online with the same exact concept. But basically, in order for the rubber band to stretch out the way this works physically, in order for it to stretch out, it has to expend energy, and it doesn't want to expend energy, so therefore it prefers to stay in the middle like this. If I'm remembering the explanation correctly. If I'm not remembering the explanation correctly, you can go watch their videos. By all means, watch other people's videos, because the better everybody does on YouTube, the more content we get. So anyway, for the pulley, what will I do? So I got to make a decision right now. So I'm going to go ahead and I'm going to so the only thing, it's not that difficult to print. I'm just thinking about how difficult it will be to print a rounded surface, and it's really not that difficult. There's a little bit of overhang is what I'm thinking about, but it's going to be so subtle that it really doesn't matter. For example, these guys also have overhang, obviously, and it's probably going to be less than that, so it's probably not something to worry about. So yeah, I will just go ahead and print the pulleys out. Now, because I'm printing pulleys to go on this, my minimum size is probably going to be on the furthest on the outside, 22 plus 10, let's say. So 5 millimeters on each side. Does this sound right? So basically what I'm looking at, again, since I have paper, I can explain things drawing more easily. I'm going to have my bearing on the inside here. And then I've got to add some amount of material around the outside. And it's going to build up to the center point. This is going to be a center point, but it's got to build up to that, right? So in order to have a full layer, here, at the very minimum, I need 1 millimeter. I probably want to have like 2 millimeters here as my minimum layer size. 1 millimeter leaves me a little bit concerned that it's going to fall apart, but 2 millimeters I'm perfectly a-okay as a wall thickness. I should use the term wall thickness, that would make more sense. So if this is starting at 2 millimeters wall thickness, and then I got to add more in order to encourage the rubber band to stay in center, I figure, I say another 3 on that side. Maybe it should be more like 4 or 5, in which case will be 2 plus 5 equals 7, right? So it will be a total overall size of 7. So at that point, that would be 22 plus 7 on one side plus 7 on the other side to get the full diameter is 14 and 36. So in that case, my smallest diameter that I can have is 36, And all my ratios, for example, this 1:2 ratio would have to be 36 minimum. Again, it could be anything above that. I could actually make this 45 so long as whatever's on the other side is twice it. So 72. So that's what we're looking at. And again, that assumes that I want the difference between the smallest distance on the between the smallest distance at the top and bottom and the bulge in the center of 5 millimeter difference. That would be 7, and then the 7 again, you need a diameter, so it's 7 and 7 on each side to get you 36. That might have been a little bit over explained, but good enough. So there is a couple of things here. I just realized I was so concerned about these spinning, right, that I realized I was being in it. Oh, sorry. Wow, that probably hurt. I apologize. I hit the microphone. I was so concerned about these spinning that I was being an idiot. It occurred to me. So these actually are not supposed to spin on the shaft. My pulleys are supposed to be spinning the shaft. They're supposed to be applying spin to the shaft. In which case, they're going to be a good bit smaller than this 24 or this 22 plus 14 for 36. So it's going to be a good bit smaller than that. Instead, I'm going to stick with that 24 because this pulley needs to be fixed to the shaft, driving the shaft on both sides. And therefore, I'm not using the bearing, and therefore, that entire discussion we just had goes out the window. Nice. Okay. Let's get on to doing something productive. Oh, goodness. Let's turn these back on so I can see. Actually, I know it's going to be intermediate shaft 1. Yeah, that's going to be the one we're working on right now. That's the one in line. As I was saying, so the next thing I was getting at, back to the teeth, 24. Okay, so here's one thing we can do. We can actually go smaller than 24. I was saying I will just stick with 24 to make things easier. There is value in going smaller than 24, and that is because we can avoid these teeth. So in theory, at 24 millimeters, let's see what it looks like, just so that I'm not talking out of turn here. New component, pulley. Actually, let's back up. Yeah, I keep on saying I should probably stop that. This guy, that guy, nope, not that guy, this guy, there we go. This guy should not be tangent to that guy at this point. That guy should be tangent to our new multiplex gear. There it is, PD. Yeah, that's right. So why aren't I seeing it? Oh, it is there. I just, very difficult to see. There it is. So instead of being tangent, this is the old one. This is the 16 tooth gear. We are now going to be tangent to that guy right there. And finish. Now this is going to not, what I should have done before I did that is I should have put a joint on this guy to keep this guy solid with that guy. And I should be doing that for all of these. Oh my goodness. I apologize. You were just staring at the desktop for the last couple of minutes while I was talking about Fusion. So let's back up just so I can show you what happened there. back, 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 back. Yeah, there we go. So this was my tangent previously. This is the 16 tooth gear right here. This was my previous tangent being tangent to that. These are the pitch diameters for both of the gears. That's where they mesh. That's the point at which they mesh, and that's why they're tangent. I no longer am using that 16 tooth gear. I'm using this keyed, well, D-shaft 8 tooth gear. And therefore, instead of being tangent to that right there, let's go forward. I want to be tangent to that guy right there. So that shifts this up. And what I started to say is, before I did that, I really should have all these gears joint to their shafts. That way, anytime I move one, it should move together. Although I'm not moving this one, I'm changing where it was originally drawn. So that actually will not fix my problem. Nice. Regardless, let's just get this guy repositioned. Roll here. Let's find out where you're at. You're right there. Okay. Get you repositioned. Whoops. Reposition you on that. Okay. And you want to be, because you're our first gear, you want to be in line right there. Cool. All right. So that gets us back here. Now, back to what I was talking about. With this pulley that I'm about to put in here, by not having it be, let me find the output shaft, and actually that output shaft has to also be moved. That is not correct. Where is my output shaft? By using a smaller pulley that avoids these teeth here, this outer edge, we therefore can have the pulley on the same shaft as this intermediate shaft and have that driven. So that's what we'll do, and therefore we won't be using the 24 because the 24 millimeters is this line right here, and as you can see, that line will interfere. If I make the pulley the same size as that line, it will go right through these teeth right here, which means that as this multiplexing gear goes upwards, it will collide with the pulley. We don't want that. We want it to clear the pulley, and therefore it has to be smaller than this distance here. So let me get this output shaft. Actually, we don't actually need to move the output shaft just yet. So let's hop over to the intermediary shaft, and we'll leave the input shaft where it's at right now. We are going to create a pulley. We have that created. And we are going to, honestly, I'll just have it, you know, it could be really close, to be fair. I'll just leave a millimeter worth of space in between. One of those things, in real life, this is going to change a little bit. These are going to be moved up and down because real life is not the computer and things do not always line up correctly. But in the computer, at least, we're going to go ahead and turn everything off. Now, this is a 8 tooth gear, which is the same size. So I'm just going to really quick size this up. Okay. And I want this to go through there. I'm not actually sure which is outside there. I just picked that point, which sounds right in my head, but I can't be entirely sure. Regardless, okay, so this is saying 30 millimeters. So we know that from over here, and you know what, I should just include this anyway. This would be the smarter way to do it. Where's my gear at? There it is. Turn the gear off. This is the smarter way to do it. Okay. So that's where our tooth, that was less smart. I hit the escape key again. That is where our tooth nominally in space is. Again, things can move. Things may not be exactly the same place as we expect them to be once we get to the real world, but that is a good starting point. So in theory, our pulley just needs to be shorter than that, and chances are we'll be fine. And chances are if we make this, 1.5, or let's make it 2, well, let's see what that number looks like, I should say. So yeah, that's a 15 millimeter pulley. So if we call that 1.5, we get an exactly 15 millimeter pulley, and 15 millimeter is a nice round number that I feel happy with. So that's going to be the largest portion of our pulley. The smallest portion of our pulley, again, I'm going to call this 5 millimeter distance. That makes it smaller than the shaft, so that is not going to work. Let me give myself back some distance. So this is not going to be exactly 15 millimeters, so it's not going to be aesthetically pleasing. And we are going to make this work. So I'm going to just leave my 2 millimeter wall around the shaft. It's technically going to be a little less than 2 millimeters because I'm going to put in my offset for 3D printing, as I've talked about before. And that will give us a change in elevation of 2 millimeters. And that's what we're going to have to live with, unfortunately. So that is where we're at now. The pulley itself, I'm going to see if I have a rubber band around here. Otherwise, I've got a rubber band, okay. Well, I have a piece of rubber band at any rate. It's broken. I can measure this really quick, and let us say that this rubber band is, it's about 6 millimeters. We'll call it 6 millimeters. It's technically a little under, but 6 millimeters. If our pulley is bigger than the rubber band, that's absolutely fine. It's actually preferable that our pulley be bigger than the rubber band. So we'll even go a step further and call it 7 millimeters. So we're going to have a 7 millimeter pulley. That's the height of the pulley. Half of 7 is 3.5. So I'm going to go ahead and let's see our pulley construction. There it is. So 3.5 is going to be our middle. And then I'm going to go ahead and transfer this drawing over. So that guy right there will get transferred over. That's our outer line. And just to make things a little more clear, finish sketch. I'm going to convert some construction lines really quick. And I want that to be a construction line 2 because we're about to use the loft tool. And sometimes the loft tool gets a little funny with, okay, those are both construction lines, good. When you have holes in the middle, it's easier to make a solid object and then put the hole through it for the shaft than to try to make the loft with the hole in the middle already. So actually I'm gonna go one further. Stop it. Because we don't actually need this one right now, and I'm projecting it anyway. There we go. All right. And then from that one, we can go another 3.5 and do another drawing. And the reason I'm doing this instead of mirroring it, so potentially what I could have done is I could have done the bottom half and then mirrored the bottom half up to complete the pulley. The reason I'm not doing that is because if you loft across these three, you can make it round. Whereas if I loft between the first and second layer and then mirror that on top of itself, it's going to have a cone instead of a round shape. So it will be a cone up to the middle point, have a sharp edge, and then it will be a cone back down. So that is why we're doing 3 separate layers and lofting off of that. So we have our 3 layers. We'll do our loft, boop, boop, boop. And you can see that makes a round shape. Whereas if I get rid of this top layer, that makes a cone. So this cone is what we would have had. And then we would have mirrored that, and you'll see, you can imagine that's going to be a sharp shape. Whereas the second we add the 3rd layer, we get a round shape. And again, that shape is supposed to, from what I've been told, help keep the pulley in place. Again, our alternative would just be use a round pulley, which would be perfectly reasonable. Use a round pulley and then just put a lip on it to keep the belt in place, which is, if you ever looked at pulleys, how most of them are designed, right? Most of them are triangular shaped. The belt is triangular shaped. It's not perfectly, it's trapezoidal, but I mean to say it has a angle to it that keeps it inside the groove of the pulley, keep the belt inside the groove of the pulley. That's how they're normally made, but we don't necessarily need to do that because we're using a rubber band, and the rubber band will want to stay on this pulley as is, as I understand it. Now, it's one of those situations where my knowledge may not be perfect here, and therefore the pulley is going to be, let's say, this angle right here, this round angle might be too much or something like that. I might find out it's too much, and therefore the pulley still slips off. It doesn't actually stay in place, and I actually need a more shallow angle in order for the system to work. I'll cross that bridge when we get there, but for the time being, it will work as far as I'm concerned. Going back here, I'm going to turn this back into a regular sketch line. Obviously that doesn't screw us up here because the drawing or the loft was made with the original one, and therefore Fusion is useful, and the Fusion says, oh, that profile was inside of the other profile before you separated it into its own profile. This profile was part of this larger profile before it got separated off, and you selected all this area before for the loft function. Therefore, I updated the loft function. If we go into the loft function right now, you can see that this inner profile is also selected. So there's actually 2 selections here for the bottom layer. It automatically did that. So that's why I can go backwards and change that back. And now we just do our good old symmetric distance all and make sure that we're not cutting anything we don't want to. All right, so that is our pulley. Again, our pulley on the outside is 15.5, I believe we ended up with. New offset, minus 0.05. Again, that's my 3D printing offset. And let me just double check this sketch to make sure I was correct about that. Diameter 16. Right, because I took half off of each. So it was 15, I took half off of each side. It took half off the radius because I was using the offset, and therefore it is 16. So with 16 as our new pulley on this gear, we now need a 32 to have a 1:2 ratio on the output shaft. So let's hop up here. Next thing I should mention, obviously this is just kind of sitting here. It's not actually tied to the shaft. And I should probably take care of that. I was thinking about taking care of that later, but let's take care of that now. So a couple ways we could do that, and oh, well, actually, I take it back. We decided already that we were going to do D-shafts, so let me just redraw this profile and do this. And tangent, 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 that, and my D shaft that I made for this was 7.1 is what I used as the center, and then I loosened it up. Oh, Windows sounds. Sorry about that. Then I loosened it up, and let me get the music back running because that just made me notice that we're out of music. Probably was like that for like an hour now. Then I offset the face to make it fit. Point being, so let's fix that. That is now a D shaft. That is now tied to the shaft. And I'll go back and change the gear that's in there so that it is... Why did music not start? There it goes. Alright, and I'll go back and change the shaft later on so that the shaft and the gear on the shaft, which I've already 3D printed, is tied to the shaft. So now that we have that done, we can go ahead and go to the output shaft. So the output shaft at the same exact height as this pulley, we're going to want to put a pulley for it to connect to, and I'll use the bottom of the pulley instead. And again, this pulley is going to need to be 32, which is twice as much as the actually construction should be on the pulley itself. Control Z, Control C, Control Z. New component. I'll put one pulley. Okay. Construction. There we go. Okay. Make everything visible. Select that. Put that there. Now pulleys are round, so I actually never need to specify this pulley relative to anything other than the shaft. So for each pulley I make on this output shaft, it only needs to be specified relative to the output shaft, because the pulley obviously will, the belt will go in whatever direction the pulley is. So there's no orientation necessary. So this needs to be, as specified, 32 millimeters. That's our largest point. And then our smallest point, it's one of these things, we should probably make this, so I have the advantage now of having extra space because this is so large, so I can make this whatever I want. I think I'm going to go ahead and just leave it at 3 millimeters. And we'll see what happens with that. Again, one of these situations that I'm not familiar enough with to know whether or not it makes a difference. And therefore, we're going to experiment. So let's do that. Let's do that. And we'll make all these construction lines for now and come back and fill them in later. And that's 7.1. And okay, so this time on the previous one I had 2 circles here because I selected the face of the shaft, so that gave me edges, 2 edges. This one it looks sorry, I should say the side of the shaft, the face on the side of the shaft, the cylinder of the shaft, which gave me 2 edges. This one only gave me 1 edge, I'm assuming because I just did the top face, which only has 1 edge. So that sets us up for success there. Again, we're going to go ahead and off of this construction plane, go up another, well, we're going to make them all the same size at this point, right? So this is going to be up 3.5. Even though this pulley is so much larger around, it has so much wider, bigger diameter. I should use that term. Even though this pulley has a bigger diameter, it's still going to be the same thickness as the other one for now, unless I decide I need to change it. And then we go up another 3.5, 3.5, and project that. Okay. We'll do our loft like last time. All this is very straightforward, repetitive. Thankfully, can't screw it up. New body. And then, just like last time, I'll come in here, change these back to solids. Sketch lines, more specifically, is the correct term for it. And then use that to cut our shaft for. And again, I want to make sure that the shaft is not actually getting cut, it's just the pulley itself. Output, let me get rid of these sketch lines here, let me get rid of that shaft there, or offset, I said output, minus 0.05, there we go. And now we have completed the very first of the output assemblies. So let's look at how this is set up. Helical gear there, and then motor housing, etc. drive. So at this height, it's not specifically this height, it looks like these are a bit misaligned, and oh yes, at this height I didn't make the second gear here, the second gear. So there is another gear below this gear that is being driven by the drive gear. That would be the green gear in our example. So our green gear in our example is driving the red gear. The red gear is tied into this one because this is D shaft. This red gear is now driving one of the blue gears, right? We had those blue gears there. And that blue gear is tied to this pulley via the D shaft again. This pulley is then going to have a rubber band stretching from here to here, which is acting as the belt on the pulley system, and that is driving the output. And that completes our first assembly. So obviously this is our 1 to 2 here. To go faster, we can go ahead and leave this as a 1 to 1 on the next one. So on another set of gears, for example, the fast shaft, which I have over here, this guy over here with this gear, he'd get a small pulley like this, and again that allows him to be on the same shaft, so we're good with there. So that will have a 1, and that will have a pulley that it's attached to over here that is also a 1. That way we are a 2 to 1, right? This 16 to the 8 here, 16 to the 8 here is 2 to 1, and then 1 to 1 and 1 to 1 is all, you know, that all multiplies out to 1s. So we're twice as quick on this one. Conversely, for the slow shaft, which I don't have in here yet, for the slow shaft, all we have to do is well, what we would do, I should say, is take this gear, mesh this gear over to another 16 tooth or a 32 tooth. It depends how exactly you want to go about it. So if we go to a 16 tooth gear, that would get us back to a 1 to 1 because it's 16 to 8, 8 to 8 is 1, and then 8 to 16 is half, 1 over 2. So 2 to 1 times 1/2, ignoring all the ones in the middle, get us our 1 to 1 back. So we're back to 1 to 1, and then we can go from that 16 tooth, let's say, so we're at 1 to 1, to a small pulley over on here on this side. So we'll have a larger, let's say 32, one of these guys, size pulley over here going to a smaller one of these guys right here on the output shaft, and that would be a 2 to 1. So every 2 rotations this does only moves this one. That's slower, right? This one is going slower than that one. So that will get us a slow shaft. And then the only last one to design would be the reverse shaft. Now, if we look here, this is clockwise, counterclockwise, clockwise, counterclockwise. So this one is, or actually, that's the wrong shaft. Let me get the right shaft up. Where are we at? Oh, do I just not have the body showing? There we go. So clockwise, counterclockwise, clockwise, counterclockwise. So technically speaking, in this pattern, so for any of these gears that only use this shaft, they are going quote unquote backwards. Now, backwards is only relative to whatever you're seeing. So if the fast, slow, and regular speed pulleys are all going in the same exact direction, then that means that that is quote-unquote forward. Even if that's counterclockwise, that would be quote-unquote forward. And to fix it, which, you know, if this is moving clockwise, I haven't actually checked whether or not the... let me look at it really quick and use my memory. Yeah, okay, I think the turntable does move clockwise by default. So, the turntable, if it's moving clockwise by default, all of our outputs will be counterclockwise. Again, that is absolutely meaningless to me. I don't really care because I'm recording for a video, and again, all this is for fun. It's not actually necessary because in the video editing, I can have this go forward, I can have it go backwards, I can have it move faster and slower just with video editing because it's all real footage anyway. I'm not going to be in the shot when the turntable is set up. It's just for display. So it doesn't matter to me, but if it did matter to you, what would basically need to happen is we would, instead of this being the output shaft, this would be a intermediary shaft for the fast, medium, and slow pulleys. And then this would go one more time to the output shaft. And that would reverse us back to clockwise. Because again, every shaft, whether it's fast, medium, or slow, well, fast, regular, or slow, all of those, as far as we are designing it, as far as we're visualizing it right now, in theory, they can be made with the same number of pulleys and, well, I shouldn't say that because it depends on the spacing of it. So technically speaking, all right, this is getting a little bit rambly, but the point being is that the only thing we got to do is tie all the shafts together that end up being clockwise to the output shaft in such a way that it ends up being counterclockwise. And that is easy enough to do. It just means, you know, for example, this guy is going counterclockwise right now, so we just need to take this guy, this shaft right here, can no longer be the output shaft. This shaft, if we want the output to be clockwise, now has to be a counterclockwise shaft, and we can drive this shaft, technically speaking, with other pulley systems. It doesn't necessarily matter. So, for example, if the slow pulley system ends up only needing one because we can fit a small pulley in here and then go to a bigger pulley there. Actually, that's the fast one. I think that's the fast one. That can have a small pulley here going to a even bigger pulley on this guy. That would also be counterclockwise, and then we can throw another pulley going from this counterclockwise shaft to the output shaft, and that makes sure that the output shaft is now going clockwise. Since I have paper, I'm going to go ahead and just draw that out really quick. Probably what I should have done before, but again, live and learn. And my other paper is getting kind of full, so I will just draw this one last time. So right now we have drive gear, multiplexed gear, and then for our example, on the normal on the normal speed, we have the normal speed shaft with a pulley on it, and then that pulley goes to one more shaft to get us back to 1-to-1. Big, small, small, so this is 1, and then big, so 2.5 gets us back to 1-to-1. So if we look at this, this is clockwise, counterclockwise, clockwise, counterclockwise, which means that this cannot actually be the output shaft. This is actually going to have to go to an output shaft, and this output shaft must only be driven in the direction we want it, which is in 3 of the 4 cases clockwise. Now, actually I shouldn't draw that. For our next one, and this would be the fast one for the fast one can also have a small pulley, and then it can go to a small pulley. It can go to a small pulley on this shaft. Shouldn't draw that there. And if I was using pencils, I'd be able to erase. Lesson learned. So this attaches to this pulley on this shaft. This attaches to a small pulley on this shaft. These both have the same number of jumps, right? This is clockwise, counterclockwise, clockwise, counterclockwise. So this is still alright going to that output pulley. That output pulley will still be clockwise. For the that's the fast one. For the slow one, unfortunately, we will not be able to put a large pulley here, because we can't put a large pulley on this guy, because that would run into the other shafts. So we'd want to throw another shaft over here and put a large gear here, and that would be the easiest way. We can just mesh these two gears, and then from this large gear, so we got large, small, 2-to-1, 1-to-2, let's say. So that gets us back to 1-to-1, as I was talking earlier. We'll have a small pulley, and that can go to a large pulley on the output gear. And that large pulley on the output gear, if we look at this, clockwise, counterclockwise, clockwise, counterclockwise, we're still going clockwise on the output gear. We now got this large pulley on the output gear. That is now a small pulley, so a 1 to a large pulley 2. So that is our slow pulley, right? Yeah. All right, cool. Now the reverse gear. The reverse gear, we want to be a 2-to-1. Or a 1-to-2 rather. A 1-to-2 on going from this intermediary gear to the output shaft. If we count these, we're clockwise, counterclockwise, clockwise, counterclockwise. That's actually the direction we want to go, which means that we can just put another large gear just like this, another 2 on a 1 pulley here, and then connect this straight across to that. So that is how we would work out how exactly to make all these. And again, I'm trying to keep these streams a little bit slower. We're just about to hit the hour-and-a-half mark, and therefore I'm not going to draw all that up in Fusion, because all the rest of this is repetitive. It is doing the same exact thing over and over and over again, and that's actually something you can figure it out yourself based on everything that we've done. Again, not the point of the stream at this point for me to actually do all this. There are other types of streams that I've talked about, the actual workflow stream that I've talked about, where, you just tune in to see what I'm working on, or I tune in to see what somebody else is working on. That kind of stream, obviously, that would probably have a lot less. And I should say, since I'm tuning out now, closing the stream, getting ready to end the stream, etc. I'm going to be putting together a video detailing the channel, what content I'm going to have up, the formats and whatnot, and I'm going to use that as the landing page video. And in that, I'll talk about exactly what I'm talking about here, about what I would like for the future for long format videos, and how this type of format video, where I'm consistently talking to the microphone, is not going to be the same thing. How this is going to be basically general workflow, as much as I can include without being repetitive. But like I said, that's a conversation for another video. So that wraps up this video. Thank you for tuning in. I hope you found this useful, and I plan to, as I suggested, continue doing hour hour and a half, let's say, maybe as much as 2 hour workflow videos like this, where I detail everything I'm doing, so long as it's not getting repetitive. And I'll go into more detail about, for example, I did a programming video that is not currently live, it's not currently public. I privated it because it was not good quality. And I'll go more into detail about that in another video. But not every live stream that you see that's intended to be a workstream video, I just give you a heads up, will be kept public. I plan on actually doing supercuts of the ones that end up being too repetitive, because one of those things, while I plan to do these workflow videos in a way that they are not repetitive, sometimes they can end up being too cumbersome. For example, having to constantly go back to API in the programming videos, that does not make for good content. So I'm going to go ahead and attempt to sign off one more time and not go into a tangent. So thank you again for watching the video, and I hope you have a great afternoon, day, evening, wherever you're at in the world.